Okay, so in this triangle, notice we're given all the side lengths. In right triangle ABC, AB equals 20, AC equals 12, and BC equals 16. So when you're setting this up, right, here we have 12, the hypotenuse needs to be 20, and think about why that is, right? The hypotenuse has to be 20 because the longest side is always the hypotenuse, and that's the longest number here. So we have 12 and 16 and 20. If we scale this triangle down by dividing each side by 4, we would get 3, 4, 5. This is a classic right triangle. Excuse me, but oops, fix that. But that might not help you because if you think about or take a look at this problem, right, they're not asking you for side lengths, they're asking for the measure of an angle. So as soon as you see that, you know that this needs to deal with something else. So this is where we bring in our trig ratios for right triangles. The sine, right, of an angle, let's say we call angles theta, always is equal to the ratio of the opposite side of the angle over the hypotenuse. And this is just a ratio. That's all sine is. It turns out in every triangle that looks like this, right, or every right triangle that looks like this, if you look at one of the angles, right, and you take the ratio of the opposite side of the hypotenuse, you always get the same ratio. So let me fix that. So it's just saying, again, sine saying that the ratio of the opposite side to the hypotenuse side across from the angle you're looking at is always the same. And you could also use cosine, right, in problems like this. The cosine is the name for the ratio of the adjacent side to the angle you're looking at, right, over the hypotenuse. So these are just ratios. These are words for ratios. Instead of saying every single time, okay, you're looking at an angle, say we're looking at this angle right here, right? What is the ratio of the adjacent side? The adjacent side is the side that forms the angle. You're not going to use this side over here, that's the hypotenuse. But the cosine is just a word we use to describe the ratio of the adjacent side to the hypotenuse, right? So every triangle, in every right triangle, the cosine of this angle in this position equals the adjacent side over the hypotenuse. And notice in this larger triangle, what's that ratio? Well, the adjacent's 12 over 20. So the cosine of theta here, right? In this case, the cosine of theta, sorry, this symbol is theta, it's our variable for angles, equals 12 over 20. But this is the same in every triangle, because if you look at this right triangle, sorry, it's the same in every right triangle that's similar to this one. In this triangle, the same angle, if we take the cosine of theta, what happens? Well, again, adjacent over hypotenuse, so that's 3 over 5. But notice, right, and 3 over 5 is equal to 12 over 20. This means what? This is just pointing out and that the cosine of the angle is the ratio of the adjacent to the hypotenuse, and in all similar triangles, the cosine of any angle is equal. And lastly, we have tangent. Tangent is just another common ratio, right? Sine, cosine, tangent. Now, tangent is equal to the ratio of the opposite side, right, over the adjacent. So these three constant ratios pop up in similar right triangles. It's got to be a right triangle. And you can remember this by, I think it's helpful, SOHCAHTOA. You can even write it like this, SOHCAHTOA. You just say it over and over again like a mantra in your head. This acronym here, SOHCAHTOA, represents the ratios the ratios and what they mean, right? It shows you that sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and TOA, T is for tangent, and opposite over adjacent, right? So it shows you what those ratios mean. That's just a little bit of background because here all they want to know is the measure of angle A. So we have choices. Let's look at this. So AB is 20, BC, right, is 16. So here's B and here's C. It's BC. So it's A, B, C. AB is 20, BC is 16, and AC, right, is 12. Sorry, I messed that up. Let me fix that. A is here, right? AB is 20, BC is 16. So this number down here, sorry. Let me redraw this triangle down here because that's going to confuse you. Okay, sorry. So we'll redraw this triangle. We have triangle ABC. Oops, wrong tool. Okay. So you have A, B, C. And AC is 20, AB is 16, and BC is 12. Okay. So they want to know what's the measure of angle A. So angle A is right here. This is the unknown angle. Well, we could do several things. Let's look at this. If we took the sine of angle A, that would equal the opposite side from the angle. In that case, this is this side right here. It's opposite the angle. 12, oops, 12 over the hypotenuse, which is 20. You could take the cosine of A, right, which is equal to what? Well, so katoa. Ka is for cosine, so it's adjacent over hypotenuse. This side here is the adjacent. Again, I know there are two lines adjacent to, or next to the angle, but the other side is the hypotenuse. So here you use the adjacent, 16 over the hypotenuse, 20. And toa, right, for tangent of angle A equals opposite over hypotenuse, right? Or opposite over adjacent, excuse me, 12 over 16. Now this is confusing, right? Because these are different ratios. But the tangent and the sine and the cosine, right, it's not that they're all equal, it's that the ratios of opposite over hypotenuse, all the sines of angle A between this triangle and any other triangle, are all going to be 12 over 20 or some scaled up or scaled down version of that. The cosine, or the ratio of the adjacent to the hypotenuse, is going to be different than the sine, but in other triangles that are similar, it'll also be equal to 16 over 20. And the tangent of angle A is always equal to the opposite over the adjacent, a different ratio in this case, but in other similar triangles, that ratio will be identical. Now, if that's true, you can imagine that, if all right triangles have the exact same sine ratio, cosine ratio, and tangent ratio from this angle, and they're all right triangles or similar to this one, then you can tell what the angle is. And here, we kind of pull up what that angle is, right, by using the sine, cosine, or tangent function on the calculator. Just press mode here, and you want to make sure you're in degrees, not radians. So scroll down. Here, radians is blinking. I go to the right, select degrees, and now I'm in degree mode. Hit second and mode again to quit. And now we just find what that angle is. So the sine of what angle is 12 over 20. That's what we're going to do. How do you do that? Well, it's kind of like inversing the sign. You're going backwards. You're saying, I know what the ratio is. I want to know what the angle is that gives me that ratio. So you press the second button, in this case, when you're trying to find that angle. And let's use sine as an example. It'll say sine to the -1 power. That just means it's like the inverse of sine. So the sine of what angle is 12 over 20? You enter that in, close parentheses, press enter, and there's your answer, 36.86989765. And you get these nasty numbers because with these triangles, right, you're dealing, right, with often unfriendly ratio numbers, or unfriendly angle measurements, or unfriendly or irrational side lengths. Here, right, they want us to round to the nearest degree. So let's go back and take a look. That means here would be 37 degrees. So here, right, that means angle A equals 37 degrees. Now let's just confirm though that if we took the cosine, or the inverse of the cosine, second cosine of 16 over 20, we'll get the same angle measure. And we do, right? 36.86. And if we took the second tangent, or the inverse of this ratio, 12 over 16, we get that same angle, right? Because all right triangles that are similar to this one, the ratio from that angle, from the 36.86989.765 degree angle, the tangent ratio, cosine ratio, and sine ratios are equal in all of these similar triangles. So this might be a little confusing. It's a good start for many people here, but we're dealing with these ratios now, and we're looking at trigonometry. So I hope this helped.